Okay, so if you're having to watch this video because you're not in class the last couple of days, we started into our Unit 6. It's on gravity and electromagnetism. And the first day, we'd gone through some things related to just looking at Newton's universal law of gravity. If you're having to watch this video at home, we filled in some of these things talking about the universal law. And again, with missing class, all you can really get is just the details of this. Make sure you're looking through your book to pay attention to some of the details surrounding this equation. And then we finished yesterday's lecture by doing that problem that you see up top. And right now what they're doing is they're going to try problem number 2 to try to calculate the weight of that green person on the moon. Okay, so if you're just joining us, that's where we are. Okay, you try it, see if you can get through and do that work. I'm looking for that person's weight on the moon using the universal law of gravity. So as you're going through this, folks, one of the challenges that I've seen in the past with kids of your caliber, and you guys are great kids, but you sometimes struggle with using that calculator correctly. So you have some really big numbers, some really small numbers. You've got to do some division of things that are squared values. I've seen a lot of challenges with solving these kinds of things. So make every effort to try these calculations on your own. Don't assume you're going to get these things right when you go to do them on your own on the test or something. Practice it. See where those mistakes are so that you can get those issues corrected. You should have a calculator. You should know how to use that calculator. And exponent buttons are super important for this. They will continue to be important. Because when we look at the next law, which is Coulomb's law, we deal with some really small numbers and some really big numbers just like this. So you have to be able to do it. Okay? What'd you get for the 65 kilograms person's weight? Thank you, Nathan. What do you got? Okay, so about 105 and a quarter. Let's just round it to that. Newton's looks about right. Now that person here on Earth, would you guys agree that we've used F sub little g numerous times in the past, right? M times G, and we said G was 9.8. But now I'm going to calculate their weight a different way. So this is the way that we've always done it. Now we're going to do universal law of gravity for G, for the weight, and we're using this thing here. 105 newtons. Now, on Earth, that 65 kilogram person would weigh about 637 newtons. So we know that weight can change. Whereas the mass is sort of an intrinsic property, weight is extrinsic. It depends on the local value for G. Could you guys use that number of 105 and tell me what little g is on the moon? Could you go through and take that number 105, calculated using universal law of gravity? Tell me what little g is there. See if you can do it, and then we'll talk about it. If you can't do it, don't know how, I'll show you here in a minute, but calculate little g. Anyone willing to Anyone willing to shout out an answer? What you got? Thank you. You want to try, Kevin?
1.62.
About 1.62-ish meters per second squared. Would you mind sharing how you did that? How did you go from this number to that number? Wonderful. Yeah. Basically, you're taking that 105 and divided by the mass of that person. So 105 newtons divided by 105 divided by 65 kilograms is about 1.61, 1.62 meters per second squared. So we have now a way of calculating little g at various locations, maybe on the moon, something along those lines. I have a question for you before I go into the next topic. By the way, this is where I finished yesterday with my 5th hour, so it's okay. We're always up a little bit, either ahead or behind. How do you think we know the mass of the moon? Don't say Google it, because how does Google know it? How do we know the mass of the moon? Like 7.35 times 10 to the 22. How do we know that? How do we know the mass of the sun? 1.9 something times 10 to the 30th kilogram. How do we know these things? Do you know, Haley? Do you know how we do it?
Is it like calculated through like molar mass and being able to figure out what chemicals are used by it? Like,
It's interesting. So you're a chemistry person, I know, and you think we might do it by looking at average densities and stuff like that. What's the Earth made of, and what's the moon made of, and things like that. It's interesting. We can get a guess. We can get a guess as to like what the composition is of various things like asteroids and stuff like that by doing some spectral analysis and things like that. It's really not very accurate because we don't know what's inside of it. It's a good thought. You know how we do it? Are you talking like Einstein's theory of general relativity and stuff like that? It's interesting. Any other ideas? I'm going to show you how we know the mass of the moon and the Earth and the sun. I'm going to show you that with an experiment that Cavendish did a couple hundred years ago. I'll show you that. And so we actually calculate it using this value for G. I'll show you that today. Okay. So it's interesting. It's a pretty clever idea that we could use some spectral analysis. I think that's what you're referring to, molar masses and stuff. It's not really how we do it. Now we can get an estimate for some things using spectral analysis from like asteroids and whatnot. But the more accurate way to do it has to do with using universal law of gravity. I'll show you that today. All right, so there we go. Let's go ahead and look at this experiment. It's called the Cavendish experiment. So again, in these first couple of days, and I'm only going to spend a couple of days on gravity. I could spend a month on gravity, but we have to get other things. So this universal law of gravity is like the bare essentials. How we determine the big value of G, and hence the mass of the Earth, and the mass of the moon, and the mass of Jupiter, and the sun, is by this experiment. Cavendish measured G, and then he did that. When he did that, he measured the mass of the Earth by measuring the amount of rotation. So this setup that you see here is what's called a torsion balance. And I have a makeshift torsion balance off to my right, your left, that I'll show you what he did. It was like a bar with a couple of heavy weights on the side, hung from a cable, not suspended from this little this support here, but something that was suspended from the cable, or from the ceiling through a cable. And it could twist. And once it reached a state of equilibrium, what he would do is he'd bring something really heavy up to both sides of that object, and those heavy objects would then pull on those masses hung on that stick with a force of gravity, causing it to deflect slightly from its equilibrium position. That's what that diagram is trying to show. Now that mirror that's located on the ribbon cable acts as an amplifier. A very small twist of that mirror, like this, could be amplified using the fact that that angle would sort of make the amount that it seemed to twist grow with this sort of an amplification there, that you could measure very small deflections. And so the idea there is that if he measured how much force was required to twist at a given amount, he calculated he could measure everything else in this equation. This value, F force due to gravity, was based on the fact that it was force calibrated. The masses of these objects, well, one of those masses was that mass there, the other mass was this one here, and the distance between their centers, heck, that was this value here, like how far away they were. And so if everything here is known except for this, he was able to calculate big G. Once he did that, he was able to determine not just the mass of our Earth, but the mass of the moon, the mass of the sun, the mass of that asteroid that we thought maybe at some point 2032. Do you guys keep track of that kind of stuff? We're like, oh my gosh, this Christmas asteroid that could hit the Earth, and raise your hand, you've heard of this kind of thing? NASA's constantly monitoring it. They're like, oh, it's got a 1% chance, a 3% chance. So they're constantly looking at it. But how we know that mass has to do with knowing what big G is. Now, this is the experiment. This is how I did it. So if you guys want to come over for a second, I'll show you how this works so you can actually see what he did. So I know it's hard for you to see where you are. Come on over for just a second. Not exactly the same kind of setup. The same setup, I actually have tried to set this up before. It's a very difficult experiment to do. You guys hear the air handlers going on in the classroom? Did you guys hear that? Air currents could affect this, right? The force of gravity is so very, very tiny, so small that can't be responsible for people falling in love. That whole idea is a very tiny thing. That the slightest kind of air current, even electrostatic interactions, could affect us, and so it's a very difficult experiment to do. The Earth is pulling on that. Would you guys agree? The Earth is pulling on that. Do you agree it's in a state of equilibrium? Okay. So what Cavendish did, again, is he had something sort of get it into a nice state of equilibrium. He brought something like objects on either side of this to try to get it to twist like so. But again, that's really difficult to do. But for this here, if I bring that bowling ball relatively close to that, well, according to the theory that Newton developed, he said the force due to gravity should be equal to G m1 m2 over r squared. Well, that has mass, they're held a certain distance away. That wasn't there before, so the equilibrium should be upset, and that thing should pull down a little bit. Now, did you guys notice that went down a little? Could you see it? Yeah, not much. And then, again, it's a very difficult thing to measure. So this is far too coarse, if you will, of an instrument to be able to do that. He had to use a torsion cable to be able to do it. A very small amount of twist. You can measure that force of gravity. Now, I've seen videos. There are videos that people have done to try to replicate this experiment. It does work, but it's really difficult to actually do. But that's how we measure G. Okay, something like that. Once we got G, I'll show you now how we're going to get other things from that. So that's how we know it. Okay, the fact that Cavendish gave us the big value of G. Okay, that's the idea. All right, let's send it back. I'll show you a quick little video on it. Okay, so unfortunately, it seems like whenever I'm playing, doing a Screencastify recording, I can't get this thing to show full screen. I don't know why it is. But this particular, this is an animation of the Cavendish experiment. And so again, will you grab the lights for us over there? Thank you. That was good timing, Ty. So again, the idea, he's using a laser. He's got these two bars, or there's one bar with a couple of objects on the end of it. It's on a swivel, so things can move around a little bit. And as he brings these things relatively close, you'll notice that what that does is those masses sort of attract the other things, causes them to twist a little. And then he was able to measure just how much they twisted. And then from that, he was able to calculate what that big value of G is. And then that's basically the experiment. Okay. Now, what I want to do is I want to show you how we were able to use that value to measure the mass of the Earth. Lights off? Good? Keep on. In your math classes, I think they call this a transitive property. Will you turn and tell that person that you're sitting next to what the transitive property is in math? Just see if you remember that. Transitive. What does that mean? Right. It's like Algebra 1 or something like that. They say, oh, the transitive property. Oh, the associative property. The commutative property. Do you remember those things? Anyone willing to take a risk? You're going to go on camera here because I have the video being recorded. You think you got it? Transitive property? That is no one. All right, no one wants to take the risk. All right, here it is. I believe this is right, and if I'm wrong, I will go on record as being wrong. This is, I'm going to call this A. And I'm going to call this B. Now, would you guys agree that we've always calculated the weight of an apple as the mass of the apple multiplied by G? Okay. Now, this is just another way of calculating the same thing. So I'm going to say that's A, that's the weight. But done not through using m times little g, I'm going to do that by using universal law of gravity. I'm going to call this quantity here C. So if A is equal to B, and A is equal to C, what's the transitive property, tell me? B must be equal to C. If that's true, then B equals C. So here's B, the mass of the apple, multiplied by the acceleration due to gravity. Two things that we can measure pretty easily on the Earth. Measure the mass of the apple, put it on an inertial balance, measure how much mass it actually has. We could measure G, heck, with a pendulum, couldn't we? We could measure G pretty accurately with a pendulum and say, what's that local value? Well, those are things that I can measure. Those must be equal to big G. Thank you, Cavendish, because he gave us that value. Mass of the apple. Mass of the Earth, don't know what that is yet. And then the radius of the Earth, and then I go square it. Now, you guys are all great math students, so if A is equal to B and A is equal to C, then B must be equal to C. I set them equal to each other. What can you do at this point? Before you do anything else, what we do? The apple doesn't matter. It could be the apple. It could be that that water bottle that's sitting on it. Doesn't matter. Those things reduce out. Now I know everything up here except the mass of the Earth. So rearrange that equation to get mass of the Earth, and it looks like that. Mass of the Earth, little g, multiplied by the radius of the Earth squared, divided by big G. When Cavendish measured that value, 6.67 times 10 to the negative 11, we were then able to compute the mass of the Earth because it's related to the local acceleration due to gravity and how far away we are from the center of the Earth. I'm going to ask you guys to do that, right? Plug those numbers into your calculator. I know you could Google it. You could ask Bing to give, what's the mass of the Earth? I want you to be able to calculate. How does Google know? They use this law. Right? Give it a go, see if you can calculate mass of the Earth. If you're having to watch this from home, make sure you have a calculator in hand and trying these things because it is very likely that people will make mistakes doing all these calculations. So give it a go. Raise your hand, you got it. That'd be none. Come on, be proud. There's two. You want to try it, Xavier? Nice try. I've had a lot of people say that answer last hour. They got it wrong. Nice try. But that answer is pretty right. I know you made a mistake. I know where that mistake is that you made. What, you want to try, Haley?
Wait, what did you say?
He said something times 10 to the 17th.
Oh, I got 5.6 times 10 to the 24th.
I agree it's times 10 to the 24th, but I didn't get the other part. What did you say, 5 point what?
5.98.
Thank you. 5.98 times 10 to the 24th kilograms. Now, I think, Xavier, you might have forgot to square the 6.38. You probably forgot to square it. I can tell you're off by, 10 to the 6th, 10 to the 7th, somewhere in that area, and that's just because of that squaring factor. Again, I see a lot of people make mistakes on that. How do we determine that mass of the Earth? Haley, I just want to go to the, your idea of like looking at, would you call it, molar masses and stuff like that. The Earth has all sorts of different kinds of minerals and things like that. We can get an average value, but to be able to do a summation of all those things is really difficult to do, right? So if it's a pure value, or a pure substance, molar masses would be a great way to be able to do it, because it's uniform. But when it's a mixture, like we have a very diverse Earth here, we're not going to do that with molar masses. 5.98 times 10 to the 24th kilograms. Anyone have their Chromebook on them? They can do a quick check. Can you have your Chromebook up? Do a quick look. What does Google tell us is the accepted mass of the Earth? Let's just see how close that is.
5.972 times 10 to the 24th.
There you go. 5.97, 5.98. It really depends on how well we're able to measure that value of little g. Right, 9.8. Now, let's rearrange that equation. Let's actually calculate, get a value for g. Little g can be found then from the big G that Cavendish gave us. And so I want to know the local acceleration due to gravity on Pluto. That would be little g on Pluto. Well, we can use the universal law of gravity to be able to do that. So what is the mass of that central body? How far away are we from that central body? Now, I'm going to talk a little bit about what d is here. I've gone through and changed r to d, and I want you guys to realize that that d is really equal to the radius of the Earth plus whatever elevation I am from the surface of the Earth. So usually our h, if we're doing experiments here in the classroom, our h is 0 because we're on the radius of the Earth. They're pretty close to the surface of the Earth. But if you start going up in elevation, and that elevation is significant in comparison to the radius of the Earth, you can see g changing. And so we've said g is 9.8, but it does vary. It depends on where you are, especially if you're at any altitude. So we would say d, again, is the radius of the Earth plus whatever elevation we're at. So g does change. Now, I want to take a moment and show you some g anomalies. So if you can give me a moment, I'm going to look at how g varies on the surface of the Earth. And some of these maps are sort of interesting to look at. This one right smack dab in the center, this is Wikipedia. It's probably not the best resource for that. Here's NASA. So again, this map of the Earth is color-coded, but it's showing that those variations, those color variations, have to do with g anomalies. And so we say it's 9.8, but in reality it varies. Now you might notice some of those locations, I'm not sure the red versus the blue and things like that, but it is not a constant value. It's close to 9.8, but it does vary. So apparently these things are videos that you could watch. It's probably turning or something along those lines. But I'm going to go ahead and go back to our normal stuff here. All right, I want to go through and show you the acceleration due to gravity varies over the Earth's surface. One thing is due to altitude. Other things are local geology. Earth science, you might remember that geology is going to be studying some, maybe some changes to the value of G based on what's underneath your feet. Natural gas behaves differently than iron ore and stuff like that, so you can have some local geology affecting G. The shape of the Earth is not quite spherical. It's a little bit oblong, and that's because of centrifugal effects as the Earth is spinning. Take a look at this table over here. Again, I wouldn't ask you to memorize these things, but you should see 9.8 is pretty close to what these values are, but it does vary. And so Denver, sometimes called Mile High Stadium if you follow football stuff. So Denver, when they kick the football in Denver, it usually goes further. Like field goal kickers can kick a ball further in Denver than they can other places. The value for G there, because we're further away from the center of the Earth than normal, is a little bit smaller. Pikes Peak is a mountain in the Denver area, Colorado area, and so again, anytime you go up in elevation, you start to lose some of that value for G. Now the equator and the North Pole, you can see that at the North Pole, the Earth is somewhat squished at the North Pole, and it's elongated at the equator. So if R changes, our average is 6.38 times 10 to the 6, but at the equator is somewhat elongated, so you're a little bit further away, and so your value for G would be a little bit smaller at the equator, a little bit greater at the North Pole. All right, I don't know if we have wrestlers in here. Wrestlers? Okay, sometimes wrestlers have a hard time making weight. They're over by a few ounces or half a pound. what I would ask you to do is determine what happens to a person's weight if they fly in an airplane 30,000 feet above the surface of the earth. What's the value of G up there? So I want to give you guys a go at that, see if you can do it. I'm going to draw a quick drawing of this. It's not going to be to scale because the earth is so large compared to elevation changes. This drawing NTS, that means not to scale. If this airplane is at this elevation, (9,100 meters above the surface of the earth, then we're going to have to add that 9,100 meters to the radius to be able to calculate what the value of G is out there. Now, in making that arrow smaller, quite a bit smaller on purpose, G is a little bit less up there. This is showing that G, we always assume it to be 9.8, but it can definitely decrease as we start to go further away. So you can just set up that equation to be able to calculate the value of G at that elevation. Again, folks, get comfortable with that calculator. Big numbers using exponents, small numbers using exponents, knowing how to square, when to use parentheses, things like that. Lots of computational errors as of late. I asked the math teachers, like, yeah, computational skills really going down. A lot of people make mistakes. Check your work on it. It's not going to be 9.8, but it's not going to be that much smaller because 9,100 is not a really big number compared to 6.38 times 10 to the 6, right? So it's going to be smaller, but not that much smaller. Did you get it? How many people feel comfortable? They feel confident in their answer? About 3/4 of the class. Others aren't just willing to raise their hand. I get about 9.77. Anyone confirm me? Okay, 9.77 meters per second squared. That's about a reduction of 0.3%. So if a wrestler was having a hard time making weight, boy, you fly an airplane, you're going to lose about 0.3% of your weight. That's not much, but it is measurable. Okay. All right. I want to do one more with you. Raise your hand. You've been to the ISS? Oh, you guys are thinking I'm talking in-school suspension. No, I'm talking the International Space Station. Raise your hand if you've ever seen videos of those things, the ISS. Did I ever show a video of the ISS things inside of there? Have I ever shown that? Oh my gosh, it's pretty cool. All right, it's the International Space Station. It is, what's the acceleration due to gravity up there? Orbital height. So it's orbiting about 249 miles above the surface of the Earth. Now that distance is about from Grand Haven to Indianapolis. Now Indianapolis is straight south. This one is straight, not north, it's straight up, right? So the ISS is orbiting. at an elevation of 250 miles-ish. What is G up there? Would you guys agree that it's almost zero because things float around? Would you guys agree? Well, if you look at this, if it's in orbit up there, the force of gravity in that shuttle, is it nearly as much? Is it about half as much? Is it nearly zero? That's what we might call microgravity. Does it feel like it's zero up there? Sure looks like it, but it's not. I'm gonna queue up a couple of these videos, and I'm gonna try to get them showing so you can see what it's like up there. You guys calculate what G is. Now, if you need to do a conversion, 249 miles. I use this conversion. The conversion I use, because I don't always have access to Google. I would say 3.1 miles is equivalent to 5,000 meters, and I know that because of the cross-country runners, that you run a 5K race, but that's actually 3.1 miles. So you can do a conversion, 249 miles by multiply it by 5,000 divided by 3.1. And so that number, it's 401,000 something, and I don't remember the other portions, but once you do that, do your 249 multiplied by 5,000 divided by 3.1. What is that number for me? I didn't get 417 before. So 401, 613? Okay. Again, folks, that distance is how high up the International Space Station is from the surface of the Earth. Calculate G up there. See if you're able to do it. This is apparently a live stream of the ISS. I don't know if it's actually live or just a recording. But it's orbiting the Earth about 250 miles up. And people seem to be weightless up there, but they're really not weightless. Seem to be floating, so you'd think that G is zero up there. What is G up there? What do you guys get? Yeah, it's only about 11% less, about 8.67 meters per second And again, you're using that equation from before, but you got to add that to the radius of the Earth. So my question is why are things apparently floating up there? How many people feel, I see Nathan's going to share that's really good. How many people have a sense as to why things float in space? Just you feel comfortable with it? Just a few. Nathan, go ahead and tell us why are things floating?
It's because the ISS, the people in it, and the things in it are all falling just at the same rate in a circular pattern.
Yeah, so orbital motion is really falling motion. And so they're just traveling at the right speed to be able to be falling at the exact same rate as the Earth is sort of falling, curving below it. And so it's basically in a state of free fall. Now, I tried to, I've never been in the ISS. I've been down to the ISS room for a little bit just to see what it's like, but I've never actually been in the ISS. So what I tried to do is I tried to experiment with that myself, and I'm going to show you what that looks like. I've made a video of it, and so I'll try that with you guys so you can get a sense of that. So it's really just in a state of free fall. Now I'm going to stop there, and I'm going to stop the video.